Alright, so let's now consider some examples and trace them. And the one I'm going to trace will be the test singly linked list add in the source code, which I have made available to you since last week. Right? You can take a look at that. And I think for this one, let's now just keep it on the paper to really make sure you understand. But I can show you maybe a little bit on the Eclipse debugger if time permitted. We'll see. All right. But you can definitely take a look at that method there. All right. That test method. Let's now switch. And we are considering this JUnit test over here. And this will be our add method. And this will be the list which we are familiar with. So that'll be the input, right? You can see this part of the test over here. This part. So this part of the test will actually construct a list like the list structure that we are familiar with over here, right? That's something we'll see. All right, so this part I can skip, right? You can definitely just go over the debugger if you like, line by line, to make sure you can see exactly how the node has been constructed. I think we did that exercise last week as well, but you should definitely practice. Otherwise, whenever you get stuck on implementing new operations for a linked list, you just wouldn't know how to go from the beginning, right? So that's something I'll leave to you. Let's now take a look at the rest of the code over here. Specifically, I want to look at 3 calls to the add method. Let me highlight them first and then we'll trace one by one. The first one is over here. List.add and index 0. So that'll be the one extreme case where we're adding the first, right? And also the second one, which I'll highlight in blue. The second one will be this one over here. That will be to add index 2, like somewhere in the middle. And the last one I want to do is to add list.getSize. So you can see explicitly I'm telling you I'm adding to the very end over there, right? Notice that again for list.getSize, this index here would be considered as invalid if you're trying to pass it as an argument for getNodeAdd. However, for add, it will be okay, right? Just something you want to make sure you understand. Right, let's now consider these 3 lines one by one, right? And let's now try to do as high level as possible so that you wouldn't lose the big picture. Well, let's now start with this one over here, right? This one. List.add index 0 and then let's say Suyan. All right. So we're gonna execute this line over here, and then definitely it's a valid index because you can see I, which is 0, 0 less than 0, false. And also 0 larger than the size. What's the size right now? Right? You can definitely make a notes. The size for this particular list right now is 1, 2, and 3. Right? At the moment. Of course, the size will be incremented later. But just notice the color. At the point we're calling this line, which is green, the size is actually 3. So 0 less than 0, false. 0 larger than 3, also false. False or false is going to be false. So we don't really throw any error. So we're going to bypass, and then we're going to go for the else part. And I is equal to 0, that's actually true, right? In that case, we're simply just going to add first. And as I said, I assume you already studied the add first method from last week. So what I will do is I'll just show you how the structure is going to be changed. So what we'll do is we're going to add, what's the E over here? That will be Suyan, right? So what we'll do is we're going to create a new node over here. We're going to create a new node. Let me draw better. So we're going to create a new node over here, and the nodes over here is going to have 2 elements, 2 attributes. One will be the elements, and the other one will be the next over here. And the add first is going to make sure after that the head of the list is actually going to point to this particular node. And the next is going to point to what used to be the head, which will be here. Right, that's something that I assume you already knew from the earlier tracing for the add first. You can definitely refer to it if you have any doubts. All right. Right, so what we got so far is we actually got the head is actually pointing to over here, and then the next will be this. So what used to be the head is now the second node. What used to be the second node is now the third node, and etc. Right? And after this, of course, the size is going to be incremented from 3 to 4. Let's make a note over here. All right. So that's about the first one. Right? That one is just one simple case to show the if branch over here does work, assuming that you know how the add first works. Let's now move on to the second call, to the add. Let me use the blue over here. So what we're doing is, so at the time we are calling this, so just remember the size has been incremented to 4 already, right? So we're going to, again, execute line number 2 over here, right? And that one there, obvious. So we're going to see I will be equal to 2. 2 less than 0, false. And also 2 larger than the size 4 is also false. False or false is going to be false. So we're also going to bypass this particular throw new error. So I'm going to go to the else branch again. And now, are we falling into this special case? No, because I is equal to 2 at this time. So 2 equals 0 is going to be false. So that means we're going to bypass this block over here. So we're going to go to the else branch over here, and we're going to execute these 3 lines of code. And visually, we already explained what that really is, right? That's something you can also review just earlier, right? But I'm going to do it still again. So what we'll do is let's follow exactly line by line very carefully, right? So we're going to create some node before. Node before is going to call the helper method get node at I minus 1. So the I right now is actually 2, right? So I minus 1 is going to be just 1, right? I just did a calculation already, right? So that means the get node at is going to get the node at index 1. Index 1, well, if you think about index 0 over here, index 1, so that is going to give us this particular node over here, the reference. And then we are going to assign that node to the node before, right? So what's going to happen is the node before is actually going to point to index 1, which is the Allen node. So node before. The I minus 1th node before. All right, so hopefully so far so good, right? I didn't want to really let you lose the big picture by tracing this from scratch. I think that'll be too much. I think assuming that you knew about how this worked from the earlier part, so now you can assume calling this helper method is going to guarantee to give you that correct result. So that'll be I minus 1, which will be the node at index 1, which will be over here. All right, that's this part here. And then we're going to create another new node. And then the new node, let's put a new node first. So the new node is actually going to point to a new node object over here. Okay, so it's going to be the node, and which has 2 parts. And again, we got elements and we got next. So we got elements and we also got next, right? And the element part is going to be E. E will be UNA over here, right? So the element is pointing to UNA over here. And the next part is going to be the node before .get next, right? Node before .get next. Node before is here, .get next is this particular node. So we want to make sure the next is set to this particular node over here, right? Hopefully you can see that, right? So what I can try to do for you is you can see this .get node before .get next is really pointing to this. So we want to make sure the node new node .get next is set to this particular node over here. That's this line. All right, and 2 more things to do. Node before .set next to be the new node, right? So node before is pointing to over here. It's next, rather than pointing to over here, it's now going to point to this new node that we had just created over here. So that'll be the chain, right? And after that, we're going to increment the size by 1. So rather than 4, it's going to be 5. So which 5 nodes have we got, right? So we got the head over here, starting from the head. The first one will be the one that's pointing to Suyang. I thought I put the contents already, but I forgot, right? That should be Suyang. All right, so let me put the contents over there. It's really important, right? So this one here is really pointing to the name of Suyang. Right, just don't forget. So that will be the head pointing to the first node and the second node, and now the third node and the fourth node and then the fifth node, which is over here, right? Pointing to the fifth node. So these are the 5 nodes so far. And we got one more to execute over here, right? So bear with me. But I really hope that so far you can really see why these three lines are so important, which I already discussed intuitively earlier. But I think you really want to make sure you're convinced. You can see it's not that many lines of code we have to write for the basic operation. But in this one here, it's really calling a method that involves a loop. And we'll talk about the running time in a moment. Okay. All right, let's now handle the last node, the last line, the last call to here. And oh, by the way, so here we got one assertion over here just to make sure the list.getSize should be equal to 5, right? It makes sense. It should be 5. All right. And we are now trying to say at exactly 5, right? So specifically, list.getSize, in general, it simply tell you that it's the maximum valid index possible for the at, which means we want to insert right to the end of the list. In this case, it will be 5. We'll see exactly how that will be executed. Okay. All right, so let's now try to execute it. We're going to still do line number 2 over here. Right? We're going to evaluate the if branch over here, line number 2. Right? Let's do that quickly. So it's going to be I will be 5. 5 less than 0, false. 5 larger than the size, which is 5, also false. Right? So false or false will be false. So that means we still bypass the throw error block. Right? And then we're going to go to the else part over here. So we'll go to the if. All right. And then we'll try to check I is 5. 5 equals 0 is also false. So that's not a special case that we need to deal with. And we're going to go to this else branch over here. And then we're going to execute these 4 lines again. And why don't we do that? Okay. What's going to happen if we do this over here? When we do this, we're going to call this helper method one more time. Get node at. I at the moment is actually 5, right? 5 minus 1 is going to be 4. So what will be the node at index 4? Index 0, index 1, index 2, index 3, index 4. So this is the index 4 node. And we're going to assign that to node before, right? So just local variable. So node before will be pointing to this node. So node before. Don't get confused about the node before over here and also node before here. They are simply the local variables that we have to create every time we get to this block. So you can think about as soon as we finish executing this line over here, this blue version of the node before will just be discarded. All right, but I'm just going to keep that over there so you can still remember the tracing. All right, so this line here is just to get a node before, which will be assigned to I minus 1 node, which will be at the one at index 4, right? You can see that one there basically give you the last node, the tail node at the moment in the list. All right, the next line, we're going to create a new node over here. All right, let's do that. And when we create a new nodes, let's see, I got very limited space. I think I can just manage to do that. And the new node is actually going to point to the node over here, okay? And the node actually is going to get elements and also next, all right? Elements and also next, all right? And then what's the element right now? Element is simply just hyang over here, right? Let me just try to get the element over here, which would be just hyang. Over here. And what about the next? The next will be the node before dot get next, right? The node before dot get next is simply just null. And we want to set the null to be the next for the node the new node as well. This makes sense because in this special case, after we insert the node into that particular position, this will effectively become the new tail of the list. That means its next should really remain to be null, right? Let me say it again. Node before dot next over here, node before dot get next will just be null. So we're going to set this to be null. Okay. Okay, let me just highlight it over here so you can see that. It's a bit small, but I think that's clear. All right, that's null. And then we're going to say this particular, let's say here. So we have set the elements and we have set the next. Good. And the new node is here. And let's now go to the next line. The next line will be, we want to say the node before dot set next to be the new node. Node before over here, and we want to set its next rather than pointing to now, it's now going to point to the new node over here, which makes sense. What used to be the last node will now become the second last node over here because we're inserting to the last effectively. So we're going to say that rather than pointing to null over here, it's now going to point to, let me just try to draw a little bit better. It's now going to point to this node over here. All right, and then we're going to increment the size by 1. So now rather than 5, it's now going to be 6, right? So that'll be the ultimate size for the operation, right? So what's now ending? What would now be the ultimate list structure over here? Let's now highlight it. Okay, let me use maybe orange over here. So we got our list to start over here, and then the head is this particular node, right, with Suyang, and then its next is pointing to this node with Alan, and the Alan node is actually pointing to this new node that we created before with Yuna, and Yuna actually is pointing to the next node over here with Mark, and then Mark is actually pointing to the node for Tom, and Tom is actually pointing to this new node we have created, which is Hyang, right? Let me put one more thing just for final clarification about the indices. So in this final version over here, index 0 will be this node over here. Index 1 will be this node over here. Index 2 will be this node over here. Index 3 over here. And also index 4. And this will be index 5. Right? Let me write the 5 a little bit better. Right? So this will be index 5. And since we now the size is actually 6 and the largest index should be 5, it makes sense, right? So that's why you can see get size should be 6, right? That's not a problem, right? You can definitely try to evaluate the assertion over here, but let's just do one together, all right? What about we try to evaluate this one over here? If we simply say get node at over here, get node at index 5. Index 5 is here, which is going to return this particular node, and then we say get elements that should be equal to Hyang over here, and you can check all the others as well in a similar way, right? Right, it's a very complete tracing about how you can you can trace different input values for add. Either you try to insert at the very beginning, or insert at the very end, or insert in the middle. I show you all the cases already, right? What about the running time? Apparently, if you only look at the code itself, it seems to us that there's no loop explicitly. So you might think it should be bigger of 1 because there's no loop. Well, that's actually obviously not true. I'm pretty sure many of you wouldn't agree, right? It's actually not the case because remember in the very beginning, I forgot either week 1 or week 2, we said that should be week 1. When we talk about counting the number of primitive operations, and remember when we enumerate all the possible statements that should be considered as primitive operation, we did not include method call because we said for each individual method call we have to judge case by case. Sometimes the method call may involve a method that does not involve a loop, but sometimes it does. So now in this case, when we try to look at the running time for get node add, which we know from the previous discussion, this part over here is going to be linear. So this part over here. This part over here, we know very well is going to be linear time. And this indeed is going to dominate the rest. So you can see for the rest of the add, you can see this part over here, and also the if condition over here at first, which we also learned from before, is actually constant. And also for the rest of the setup over here, is only about to set the reference. And for that one there, it's also bigger of 1, right? So this one is going to dominate. So eventually it turns out it's still actually bigger of 1. Sorry, bigger of n. So it's still linear. Dominated by get node add. Right? That's the justification. Quickly. Is really dominated by get node add, which we know it's a linear. All right, so let's now get back to the slides and just finish the discussion for this method here. Right, a call to add may end up executing. So these are simply the breakdown, which I already spoke about, right? So you should want to know that in line number 10, which is this one over here, when we actually make a call to the get node add, so that's the one that will dominate, which will be linear, which is definitely the highest power compared with all the previous one, which is only constant. And of course, from line number 11 to 13, so those 3 lines over here, so these lines are just about getting to the next and setting some reference for the new node or the node before. So these are also constant, right? They wouldn't matter asymptotically. So again, so this will be the dominating line that you want to understand, okay, which is a method call. All right, so final question, what is the worst case of the index I for add? Well, so the larger the I is, so that means the more get next reference you will have to really call in order to get to the next node, right? Similar to the get size or get tail has similar methods, very similar, right? And what will be the largest possible value for index I? That should be a simple question for you to answer now. It should not be size minus 1. It should be exactly size, right? So that'll be the list.getSize. And we did that for tracing exactly, right? You can see here, the last call we traced, we simply passed list.getSize. So in the case where we actually got 5 elements in the list, we simply try to insert the new node as at index 5. So that, what does that mean? That means the node before should be at index 4. So that will be the very last node that used to be in the list. That will require the most work for the get node add method over here, right? Just to reiterate the point. Right, so the list.getSize will in turn triggers the get node add list.getSize minus 1, which will require the most work to really go all the way to the end of the current list. And that's why overall it's going to be linear time for the add method, because it's going to be dominated by this helper method call. You might be arguing, well, what if I don't really call this method? Well, you cannot get around. Either you call the helper method by avoiding to reinvent the wheel, or you have to implement the loop again. There's no way around. You have to get to the n-1th node, no matter what. All right, finally, let's now consider what would be the corresponding or counterpart operation in array. How would you actually insert something maybe at the front, in the middle, or maybe at the end of an array? Well, it turns out that will also be linear. So inserting to the middle of a linear like a sequence, either implemented by array or by simply linked list, they are equally efficient or inefficient because they will both be linear time, but they involve different primitive operation to be linear. Let's recap very quickly. In the case of the primitive array, in that case, it will be linear because you have to somehow create a strictly larger array and copy over all the contents and shift the position to the right by 1 position, right? That's what we said earlier. So that'll be linear. On the other hand, it will be linear for the case of linked list because you have to get to the i-1th node in order to really set the next reference and also the new node. And for that one, it's going to be linear as well for you to call the get node add helper method, right? So both will be linear, but for different reasons. You want to make sure you understand what the reason is. All right, so that's about the inserting to the middle. I think maybe for the Eclipse debugger, I will leave that to you as an exercise. It should be rather straightforward for you to do. I will try to maybe do some Eclipse exercise when we get to the later part for this week. All right, let's now move on to the last operation for the simply linked list.